thanks for letting me go a little bit sooner. I have to pick my kids up from school, so I will be around until about 3 o'clock. I think I'm going to leave. Otherwise, they'll be abandoned and they won't learn to swim. So that's unfortunate. Okay, yeah, so welcome everyone, and once again, thanks for having me. I'm from Hugging Face, and I work in the developer advocacy, the developer relations team. I'm a machine learning engineer, and most of my contributions are around post-training and reinforcement learning. And so I mainly work with the community in libraries that are using to build those libraries that we have, like Transformers reinforcement learning, and also people in other libraries that are kind of building off of our tools and to help them to grow. And I mainly contribute to OpenEnv at the moment and TRL, our reinforcement learning library. Our DevRel roles at Hugging Face are quite broad, so we are kind of engineers. We build stuff, and then we kind of go out and we speak to people and kind of collaborate by building, really. But today I want to talk to you about something that I think will be quite impactful to this community, but it isn't a project that I'm the author of. I'm kind of a user of this project, and that's the kernels community and the kernels hub, basically. And so this is a way of getting custom GPU or custom kernels to work reliably across different environments. So when I'm post-training models and when I'm doing inference, I'm a kind of strong user of these custom kernels and a beneficiary of that, and I think other community members can be. So I'll just clarify the context. I'm sure that many people in the room are kind of familiar with this challenge, or I hope they're familiar with this challenge. So when we think about deep learning efficiency, there are 3 components that we're working with: the compute, the memory, and then the overhead. Compute is the time spent that the GPU is doing math, basically, matrix multiplications, etc. Memory is the time spent that data is moved around in one way or another, shuffling tensors or any kind of operation. And overhead is basically everything else. We always assume that compute is a bottleneck here, but in most cases we know that memory is in fact the bottleneck. If we took a modern H100 GPU, or just because I've got the stats here, it could do a petaflop per second of computation, but the memory bandwidth is 3 terabytes per second. So that's a 300-to-1 ratio. So we know that if operations are fewer than 300 flops per byte, then that process is memory bound. So that includes most processes that the community are doing, right? So we know that, okay, memory is our bottleneck, and the takeaway really is that the GPU could compute 100 times faster if the data was there ready. And that's the challenge that we're working with. And fortunately, the community and science has delivered solutions to this challenge. They're available, and we can use them. And in general, what they do is they increase the arithmetic intensity. So instead of reading data in separate operations, we get the GPU, we get the system to read data once and do as many operations at once, and then write the data back. So we keep the data in this fast SRAM. And we do these as few operations as possible to a slower memory. We spend the least amount of time computing our tensors. So what that would look like is that instead of doing sort of like, x equals cos, x1 equals cos of x, we do it in one kind of line where like x1 equals cos of x, or something like that. So we do all of our operations as often as possible. And people like to say, oh, this makes the GPUs go brr, or keeps them hot, kind of metaphors like this. But we're just trying to keep the process as intense as possible. Something like FlashAttention is a poster child of this in its various versions. And it takes an O of n squared process down to an O of n process, and is being used widely by the community, right? So if you look at most of the post-training examples that you'll see in Google Colab that everyone is kind of learning from, I imagine even the previous speaker was probably using FlashAttention under the hood. And so the community is widely using it, and also facing the same kind of challenge of how long it takes to install, which I'll come back to. So this is the agenda. In the first half, I'm going to show you the Kernel Hub ecosystem and how we've built this standardized tooling for distributing kernels, so for kernel builders to use. And second, I'm going to show how you use kernels in PyTorch or in Python. And then finally, I'm going to give you an example of a use case with GPT-OSS. I'm going to be try to be quick. If I'm not quick enough, feel free to tell me to speed up or even stop. OK, so let's start with the infrastructure side of what we have and the kind of challenges that we're facing. So if you look at a kernel like FlashAttention in its various guises, 2, 3, and 4, there's a lack of unified structure. Every kernel project has its own layout, its own conventions, and there's no standard way to define a CUDA kernel. The build tools are fragmented. So CMake is used, but there's other options like Bazel and Messen, and they're used in different ways, and installing from source is slow. I think many of these people in the room experience this problem. So you have this endless build time. For example, FlashAttention can take 2 hours to install for many users and take 96 gig of RAM to actually get it installed. Finally, the support matrix that we're getting is kind of massive and ever growing, basically. So as we move through PyTorch versions from 2.5 to 2.8, CUDA versions from 11.8 to 12.8, and then Python versions, etc., it becomes a bigger and bigger support matrix. One thing that I personally like to highlight at this point is that model and hardware authors, as they release new models, are self-motivated to align new models with new hardware. And so you'll see these kind of great optimizations, like, for example, GPT-OSS usage of B series hardware, right? But as we move forward through the field, the motivation to support old, brackets cheap, hardware is no longer there. And it's the community's responsibility to take these amazing new models and integrate them on that older, cheaper hardware. And so kind of creating infrastructure around this is really a catalyst for that. That's the kind of end winner, let's say. OK, so let's look at the distribution. It's probably even more challenging. There are kernel versions. You need reproducible builds. A kernel that worked yesterday might not work tomorrow. You need to lock kernels for various versions and hardware. You may potentially need access to hardware in order to build kernels and test it. And there's the developer experience is painful and difficult, and probably sets a high bar of entry to kernel usage, and so disassociates a whole section of users, right? Most machine learning engineers that want to try out post-training might not understand how a kernel works and the kind of integrations of it, even though they can benefit from it. So this is our kind of goal, and this is where we want to get to. We want to get to a point where instead of having these users, these machine learning engineers, instead of having to be bound down by these CMake errors that are becoming a major part of their requests, that they can get to a point where they can say, give me a kernel, this is the address of the kernel, and they pull it and use it. So these are the tools that we've built and that we're using and are readily available now. The first is HF kernels. So and kernel-builder is the second. So this basically works by enforcing a predictive structure for every project. So every project will have a build directory, a build.toml, a C source for CUDA source, and a torch exterior directory for torch code. We'll make it reproducible by using NICs, which is a way of distributing packages hermetically, so you don't need access to the hardware that you're building for. And we can create these like build matrices, or build matrices, sorry, of hardware that a kernel works on. We want native PyTorch compatibility because that's what users are using, and so we also want torch compile compatibility. And we want them to be readily available and easy to share, so the largest proportion of users can get them, and we lower the barrier of entry as much as possible. I should have done it like that, but I didn't. OK, so the repo exists in two halves. There's kernel-builder, as I've just described, and then kernels. Kernel-builder is the infrastructure side, whereas if you have a kernel, you can use it to write it or share it. And kernels is the Python library that the end user uses to pull these kernels. And it's already integrated into transformers and therefore all dependent tools, so like axolotl, TRL, unsloth, but it can be used in any Python project. The documentation for this is HFdocs kernels. If you want any of the links that are in the slides, there's this QR code in the corner, you can copy that, but I'll also share them afterwards. So let's look at a kernel builder. So as I said, it's Nix based. I'm kind of repeating myself in this slide a little bit. So it's Nix based. This gives us this reproducible build. You define this like flake.lock when it builds. And so everything, all the dependencies are pinned. It works on multiple accelerator backends. So CUDA for NVIDIA, ROCm for AMD, XPU for Intel, and Metal for Apple Silicon. The authors of this hardware are working actively to kind of integrate new kernels into their newest hardware, but the community can kind of already piggyback off that and start to build new kernels and take those examples. It works from PyTorch 2.5 to 2.8 plus, and there's multiple CUDA capabilities, so all the way from V100 to H100 with SM70 to SM90. Sorry, that was off the top of my head. And everything for this is configured in the build.toml. So you'll say something like, this is the backend CUDA, this is the version, and it looks a lot like a PyProject toml, so it's very familiar to the end user as well as the user. And this is that structure. So as I said, you have this build.toml where you define everything, this C source where you put this raw CUDA code, this flake Nix where you create these reproducibilities for hardware, and then this torch exterior where you put this Python wrapping. The structure is enforced, so every kernel looks the same, and which makes the tooling possible, basically. You push a kernel to the Hugging Face hub, a lot like a model with Kernel Builder, and it automatically generates and builds for all of the support that you've declared. And you can pull it like a repository, right, with a repo ID. So the file convention uses the same naming, so you'll see like torch 27 CXX11 CU, and this declares the build environment that you've set it up for. And the end user doesn't really need to understand this. The kernel's Python client pulls all of this and identifies the right end build for the environment that they're running in. And it will also create a nice like README and the kind of project interface to say like which PyTorch, Python, CUDA variables that this package is, so the end user can access it like that. But ultimately, they'll just use a method or a function, called getKernel in order to pull that from the hub. For example, the getKernel for FlashAttention 3 takes down build on like a Colab instance from 2 hours to 2.5 seconds. And this is how they access them. So they go to the hub, they'll search for kernels, and they'll see a list of all of the kernels, like FlashAttention 2 and 3, but also other specific layer operations, like GELU, and et cetera, et cetera. At the moment, we're seeing about 31,000 monthly downloads of kernels like VLLM FlashAttention 3, which is the most popular one. So that shows that the community is really using this and that it's already saving a lot of compute time. Where should you go? Where can you find out more? A great place to go would be the hub, the Hugging Face hub, and look at the kernels community organization. That's where you can see all the kernels. From there, you can get to repositories like kernels community, which is a GitHub repo of all of the kernels that have been implemented so far by hardware manufacturers and by us, and you can look through those. And then the kernels repo and documentation is a great place to go as well. You'll notice that there's a testing suite inside kernels for builders that you can kind of pull from and use across different hardware. And so that's quite easy to use. We also benchmark all of the kernels in the kernel community repo, so it's kind of best to pull request off of that. If you want your kernel to be benchmarked along with the rest of the suite, but you don't need to. You could open your own GitHub repo and your own Hugging Face hub repo. You could in fact maintain the kernel locally and just say instead of pulling from the hub, you could actually just pull from your file system. This is some like blog posts that you can look at. There's a really cool one from 0 to GPU that just walks you through building your first CUDA kernel. There's enhance your models in 5 minutes. That's for end users. And there's an example from AMD, build and share ROC M kernels, and that guides you through building an AMD kernel. So yeah, this is just a little guide. I can race through this. Once again, you go to the hub, you pick a kernel, and then you'll see, before using the kernel, you can verify that it's compatible with your kernel. So you can run kernels and say versions for a given repo ID. So in this case, like kernels community activation is a repo ID. And it will look at your environment and match it up to the kernel on the hub, and then like put a tick to it and say like all these kernels are ready to go for you, which is handy for end users. And then you can also, in Python code, right, so if you want to use the kernel, instead of just using the regular built-in GELU function, you can just import the kernel's package, define the kernel, and then attach it in the same way or use it in the same way. And then you can verify that you have this kernel using hfcache-ls. If you use Hugging Face, also like just generally, this is a very good command. It just shows you all of the assets that are currently inside your cache, and it gives you like quite a nice handy CLI utility, so you can like just explore the models in the cache. Because for years that's been a bit of a mystery mess. Like people often build up like gigabytes of cache locally that will save them download times, but they kind of lose track of what they have, and some of it is quite useful. So if you use this tool, you can like just go through and say, oh, that's a model I actually use. Oh no, that's 100 billion parameter model that I haven't used in years. I'll delete that. This kind of stuff, and you can view that for kernels here. Okay, and then another just final example will be how you use it in PyTorch to kernelize a layer, and this can be like so not a standalone function now, but how you would like, for example, replace the forward pass with an existing torch layer. So in this example, I take CLU and mul, an activation layer which is standard in PyTorch, and I decorate it with use kernel forward from hub, and I refer to the reference. And then I declare through this configuration for which hardware I'll use my kernel, like this. So you just say, okay, for whenever I refer to this tag CLU and mug on CUDA, I'm going to go to the layer repository and I'm going to pull that repo ID. You could just as easily have like another AMD one below, and then like maybe a metal one below, and then like a CPU one below that. And then you then use kernel mapping and kernelize the layer, as you see here. So you now pull your kernel mapping and then kernelize the layer, and then you get your layer function back. So then when you pull the forward method, it will use your optimized kernel. So yeah, this is just a repeat of that. You basically decorate your layer, you define some kind of config of how you want to use the kernel, and then you kernelize the layer. And yeah, you can look up these examples and you can double check that you've used it. You can set debugging to debug mode, and it will print all the kernels that it's using as it uses them. Okay, and then the last thing, like for the AutoMagic user, is that if you're using a model like GPT-OSS 20B that has integration with kernels already, Transformers has that defined. So you can just say use kernels true, and it will use all of the kernels that were defined for that model in Transformers when you pull from pre-trained. So, and what's really cool about Transformers now, like it's a bit of a digression, I guess, but now that Transformers is fully modular, it means that when model authors like reuse the same functions, like so if they use like rope embeddings, for example, like a lot of models now we reuse Llama 4 rope embeddings. It's like the biggest thing that it's used for. And reuse Llama 4 rope embeddings, then if the kernels were defined for that rope embedding, whenever a model reuses that and the modeling file is generated by Transformers, those kernels will be attached to that that rope embedding whenever it's used. So that makes this kind of function quite powerful and keeps the modeling code quite simple for the user. Let me know if you're not familiar with what I'm talking about there and if you want to ask a question about that. Okay, and then yeah, this is how transformers knows, because at every point when that module is defined, the author would have said use kernel forward from the hub and done the process that I just described for you, like given it that tag to use that kernel. So if, for example, another model uses GPT OSS's modules, it will exist going forward. Okay, and yeah, they exist in the integrations. Okay, so yeah, let's show some stats. So this is what it looks like. On the x-axis, you've got the batch sizes from 32 to 128. On the y-axis, you've got the time to generate 256 tokens, I think. And you can see the speed up with and without kernels. But I'm sure everyone in the room is familiar with these kind of speed ups from kernels like these. But yeah, to like the end user, this is a massive speed up that they generally don't have access to. More content if you want to check out in the slides as a list of blog posts, the 3 that I mentioned earlier, plus this one that's really good, Making Deep Learning Go Brr by Horace Hay. Definitely check that out. Okay, and that's it.
Thank you.